Welcome to AI Peer Review, the deep dive where we unpack the cutting edge of artificial intelligence. Today, we're tackling what many consider the grandest challenge in AI, true reasoning. Now, we've seen incredible advancements with large language models, LLMs, right, doing amazing things with language, but deep algorithmic reasoning, the kind involving planning, searching, complex symbolic stuff that remains a really persistent hurdle. We often rely on clever workarounds, things like chain of thought prompting. But what if there was a more fundamental way? Maybe more elegant way to tackle this? Today we're diving into an interesting paper that offers, well, a pretty radical new perspective, and it takes its inspiration from the most complex system we know, it's the human brain.
That's right. This paper introduces something called the Hierarchical Reasoning Model, or HRM. And it's a bold claim, but basically it posits that by mimicking the brain's own hierarchical and multi-timescale processing, it can actually overcome some really long-standing limitations of current AI architectures. And honestly, the results they show are genuinely stunning.
Yeah, I'm really excited about this one. So our mission today, for you listening, is to unpack this HRM. We want to understand its unique, brain-inspired architecture, see how it stacks up against state-of-the-art models on some notoriously difficult reasoning tasks. And then, maybe the most fascinating part, explore the neuroscientific parallels it apparently uncovers within itself. So, get ready to have your understanding of AI reasoning deepened. Okay, so let's start there. If we look at the current powerful LLMs, despite their massive size, their incredible capabilities, what does this paper really identify as the core issue? When it comes to true reasoning, where do they hit a wall?
Well, it's what the paper really accurately terms the shallowness problem. It sounds like a paradox, right?
Yeah.
Because they're called deep learning models. But many prevalent architectures, especially transformers, possess this paradoxically shallow core. Computationally, they're quite limited. They fall into basic complexity classes, things like AC0 or TC0. What that really means, in practice, is they fundamentally struggle with problems needing sustained step-by-step computation or complex symbolic manipulation.
Right, the kind of stuff that feels more like running a program than just recognizing patterns.
Exactly. Capabilities closer to complete algorithmic reasoning, deliberate planning, symbolic stuff, not just sophisticated pattern matching. And if you look at Figure 2 in the paper, it shows this really vividly. On a task like Sudoku Extreme, a really hard version, just making a transformer wider gives you basically no performance gain. And making it deeper, well, the performance saturates really quickly. They just hit this computational ceiling.
That's a really powerful limitation. And okay, this is where chain of thought, COTI prompting, really exploded, didn't it?
Yeah.
It seemed like a way to make LLMs reason more deeply. But the paper suggests it's more of a crutch. Can you unpack that?
Absolutely. COTI is clever. It externalizes the reasoning. It breaks tasks into these sequential token-level steps. It's like making the model talk itself through the problem.
Verbalizing the thought process, yeah.
Precisely. But, like you said, the paper argues it's a crutch because it relies on these quite brittle, often human-defined decompositions of the problem. A single misstep, right? A wrong intermediate thought, maybe a hallucination, and the whole reasoning process can just derail.
Okay, so it's fragile?
Very fragile. And because it's tied to these explicit linguistic steps, it becomes really data intensive. You need a lot of examples. Plus, it generates many, many tokens for complex tasks, which means it's slow inference. And crucially, it sort of tethers the reasoning to that token level, that surface level. It doesn't allow for deeper computation within the model's internal states.
So it's making a shallow model act deeper, but it doesn't fundamentally change its core limits.
Exactly. That's the core argument.
Right, that sounds like a fundamental challenge then. So how does HRM propose to get around this, using this brain-inspired approach? What are the core principles it's drawing on?
So HRM is built on three really fundamental principles of neural computation that we observe directly in the brain. First, there's hierarchical processing, the idea that the brain integrates information over longer timescales and higher-level areas for abstract stuff, planning, while lower-level areas handle the immediate, detailed processing.
Like a conductor leading the orchestra. Higher level sets the pace, lower level plays the fast notes.
That's a great analogy, yeah. The conductor sets the overall tempo and flow, while individual musicians focus on their rapid, detailed parts. Second, there's temporal separation. Different brain levels operate at distinct timescales. We see this in neural rhythms, like slow theta waves and fast gamma waves. This separation lets the stable, high-level guidance direct the rapid, low-level computations without them interfering with each other. It maintains coherence.
Okay, different speeds for different jobs. Makes sense.
And third, recurrent connectivity. The brain uses tons of feedback loops. Representations are constantly refined, iteratively updated. And critically, this is important for training. The brain largely avoids what we call backpropagation through time, BPTT, which is the standard way we train recurrent networks in AI, but it's computationally very expensive and, frankly, biologically implausible.
Right, BPTT has always been a bit of a challenge.
Exactly. So HRM seeks to emulate this efficiency, finding alternatives.
Okay, that's a powerful set of inspiration. So bringing this into the model's actual design, you said HRM has two coupled recurrent modules.
That's right. A high-level module, they call it H for the abstract deliberate reasoning, and a low-level module, L, for the fast detailed computations. And interestingly, both are implemented using standard transformer blocks, but used in a recurrent way.
Okay, so encoder-only transformer blocks. How do they actually interact then to get this multi-timescale hierarchical thing working?
They interact through a really key innovation called hierarchical convergence. See, standard recurrent networks, they often suffer from this problem of early convergence. They basically stop computing too soon.
They run out of steam.
Pretty much, yeah. HRM, however, maintains its computational power. Here's how it works. The L module, doing the fast stuff, it converges to a local equilibrium, like finding a stable state for its current task chunk. Then the H module, the abstract reasoner, updates its own state using the L module's final converged state. And here's the clever bit. This H module update then resets the L module's context. It kicks it off again, initiating a new convergence phase towards a possibly different equilibrium.
Ah, so it's cyclical. L converges, H updates and resets, L converges again. Exactly. This cycle allows HRM to perform sequences of distinct, stable, nested computations. It dramatically increases its effective computational depth. They say up to n times t steps, where n is cycles and t is steps per cycle. If you look at figure 3 in the paper, it visually contrasts this. You see HRM's sustained activity versus the rapid decay in standard RNNs. It really shows that ability to keep computing.
That is quite ingenious for maintaining depth. But okay, back to training. These deep nested computations, training them usually runs right back into that BPTT problem you mentioned. Storing all that history, how do they train HRM without that huge cost?
Right, good question. This is where their one-step gradient approximation comes in. It's detailed in figure 4, and it's a major, major efficiency gain. Instead of storing the entire computational history, which needs memory that grows with the sequence length for BPTT OT memory, HRM uses this one-step approximation. It calculates the gradient based only on the last state of each module, effectively treating the other states as constant just for that gradient step.
So the gradient path is much simpler, much simpler. It basically goes from the output head back to the final H state, then to the final L state, and then back to the input embedding. That's it. The result. Constant memory usage. 0-1. Independent of how many computational steps you run. And that feels much more biologically plausible, too. It's theoretically grounded, by the way. They connect it to ideas from deep equilibrium models, DEQs, and the implicit function theorem. So there's math behind calculating these approximate gradients without explicitly unrolling the whole network.
Okay, O1 memory for training deeply recurrent models. That's pretty significant. And beyond that clever gradient trick, they also use another technique, something called deep supervision. You can see it in the pseudocode in figure 4. What does that add?
Yeah, deep supervision is another critical piece. It's sort of inspired by how the brain might use periodic neural oscillations to regulate learning. In HRM, they run multiple forward passes, they call them segments, within a single training example. And they compute a loss for each of these segments. But the crucial part is the hidden state is detached before it's passed to the next segment.
Detached meaning gradients don't flow back across segments.
Exactly. Gradients don't propagate across segments. It effectively creates a one-step approximation for the gradient of this recursive deep supervision process itself. This gives the model really frequent feedback during training, much more often than just waiting till the very end. And it acts as a strong regularization mechanism, too, which really helps with stability and performance, especially for these kinds of deep equilibrium models.
Frequent feedback, regularization, stability sounds very useful. And finally, to top it all off, they incorporate adaptive computational time, ACT. This sounds like the model itself decides how much thinking time it needs for a given problem. A bit like Kahneman System 1 versus System 2, thinking fast and slow. Is that the right idea?
That's exactly the analogy they draw, yeah.
Yeah.
ACT lets the model dynamically determine the number of segments, or its runtime, for a specific task input.
Yeah.
It uses a reinforcement learning approach, actually, a Q-learning algorithm. There's a specialized Q head that looks at the H module state and predicts an action. halt, or continue computing for another segment.
So it learns when to stop thinking.
Pretty much. It learns to adapt its computational resources based on how complex the task seems. And this leads to significant computational savings, often with minimal impact on performance. You can see that trade-off in Figure 5, Parts A and B, but what's even more impressive, I think, and points to genuine adaptivity, is shown in Figure 5C. It's about inference time scaling. Models trained with a certain maximum computation limit, say 10 segments, can actually gain accuracy if you let them run for longer during inference, say 20 segments.
Wow. So even after training is done, giving it more time lets it arrive at a better answer.
Yeah, it's like giving the model more time to think, and its accuracy improves. That's pretty cool.
Okay, so we have this sophisticated, brain-inspired architecture, clever training techniques, adaptive computation. How does this all translate into actual performance? We're talking about these really complex reasoning tasks, right? The ones that often stump even the biggest LLMs, which sometimes struggle with even basic logic.
Right, and this is where HRM truly shines. It really delivers a potent message about architecture. The headline results, shown in Figure 1, are just remarkable. Get this. It only has 27 million parameters. That is tiny compared to today's models.
Tiny, yeah. Billions are common now.
Exactly. And it was trained on just 1,000 input-output examples. No massive pre-training, no special chain of thought data, just 1K examples.
Okay, so small model, small data. What did it achieve?
On Sudoku Extreme, 9 by 9,
Yeah.
it got nearly perfect 55% accuracy.
55%. And the comparison.
Compared to 0% for the chain of thought models they tested. 0.
Wow, okay. And this Sudoku Extreme, it's genuinely hard.
Oh yeah. The paper mentions it's compiled specifically to be exceptionally difficult, even for humans. Far beyond typical newspaper or online puzzles. They say it requires an average of 22 backtracks for a human solver. You can see that in Figure 6, Pence. 22.
Okay, 22 backtracks. Yeah, that sounds absolutely brutal. My Sunday morning attempts definitely don't involve that much backtracking. For a model to handle that with so little data, that's kind of groundbreaking.
It really is.
Yeah.
Then there's Maze Hard, 30 by 30. Again, really complex mazes. HRM scored an impressive 74.5% accuracy.
And the Cote models?
0% again. Complete failure.
Okay, so tasks requiring planning, search, constraint satisfaction. HRM seems to excel where others fail. What about more abstract reasoning?
They tested it on the ARC-AGI challenge, both V1 and V2. This is a well-known benchmark for inductive reasoning and abstract pattern generalization, considered a step towards AGI benchmarks. Here, HRM achieved 40.3% accuracy.
And how does that compare?
Well, it substantially surpasses leading Cote-based models. They mentioned O3 Mini High, which got 34.5%, and even Claude 3.78K, which scored 21.2%.
Despite those models being much, much larger and having huge amounts of pre-training data.
Exactly. Orders of magnitude larger, huge context windows, extensive pre-training. And HRM still comes out ahead on this abstract reasoning task.
That is a huge contrast. So small model, minimal specific training data, outperforming giant models. They also have a baseline, right? A standard transformer of the same size.
Yes, the direct pred baseline, a transformer with identical parameter count to HRM. It failed entirely on Sudoku and Maze, 0%. And on ARC-AGI-1, HRM more than doubled its performance.
Okay, so the takeaway seems really clear. It's not just about scale. Architectural innovation, especially this kind of brain-inspired design, it can unlock genuinely new reasoning capabilities that current architectures, even scaled up, just don't seem to have.
That's exactly the point the paper makes. It really challenges that bigger is always better mantra. It's about the kind of computation the architecture enables.
Right. It's not just size, it's the structure. Okay, these results are super compelling. But for our technically savvy listeners, the intriguing question is, what's actually going on inside? What reasoning algorithms does HRM actually implement to solve these things? Can we even tell? It's fascinating to try and imagine the thought process.
Yeah, that's always the million-dollar question with these complex models, isn't it?
Yeah.
Getting a definitive human-readable algorithm out is, well, it's beyond the current scope, as the paper notes. But they do provide some really fascinating visualizations of intermediate predictions during the computation. These offer some crucial clues into HRM strategy. You can see these in Figure 7.
Okay, so what do those clues suggest?
Well, for the maze task, for instance, HRM looks like it initially explores several potential paths simultaneously, almost like generating multiple hypotheses in parallel. Then you see it systematically pruning those paths, eliminating the inefficient ones, the blocked routes. It forms this kind of preliminary solution outline, and then it goes through refinement iterations to finalize the path.
Interesting. Multiple hypotheses, then pruning and refinement. What about Sudoku?
On Sudoku, the strategy looks strikingly like a depth-first search. You can also see it in the intermediate grids. The model explores potential number placements, tries them out, and then it clearly backtracks when it hits a dead end in the invalid state. It iterates, filling the grid, trying numbers, correcting itself.
It's actually performing a search then, not just pattern matching a solved grid.
It really looks like it, yeah. And for ARC-AGI, the abstract reasoning task, the strategy seems different again. It looks more like it's making incremental adjustments to the board, iteratively improving the configuration, sort of like a hill-climbing optimization approach rather than the extensive backtracking seen in Sudoku.
Okay, so the big takeaway here isn't just that it solves them, but how. It seems to demonstrate an ability to actually adapt its reasoning approach based on the specific task. It's not using one single brute force algorithm. It seems to be choosing, or perhaps learning, an effective strategy for each type of problem. That's quite remarkable for an AI.
It really is that adaptability is a key sign of more flexible, general reasoning.
Definitely. Okay, let's connect this back one last time to the brain inspiration. We talked about the architectural principles, but does HRM actually develop internal structures, internal representations that mirror what we see in biology? Does anything emerge that looks brain-like?
This is one of the most exciting findings, I think. Almost poetic, as you said earlier. They investigated this using a measure called participation ratio, or PR. It's a standard tool in neuroscience to measure the effective dimensionality of neural representations.
Okay, dimensionality. What does that mean here?
Simply put, a higher PR means the information or variance in the neural activity is spread out across more dimensions. It indicates a richer, more complex, higher dimensional representation. And this high dimensionality is thought to be crucial for cognitive flexibility, for handling complex tasks. This aligns perfectly with neuroscience findings. Studies show that higher-order cortical areas in the brain, like parts of the prefrontal cortex, involved in complex thought, have higher PR values. They show this for the mouse cortex in figure 8A and B. Higher areas, higher PR.
Okay, so higher brain areas use higher dimensional representations. What did they find inside HRM after it was trained? Did this hierarchy appear?
They found a really striking parallel. You can see it clearly in figure 8C and D. After training, HRM's high-level module, the H module, operates in a substantially larger subspace. Its PR was measured at about 89.95. That's significantly higher compared to the low-level L module, which had a PR of around 30.22.
Wow, so a clear difference in dimensionality between the high and low levels.
A very clear difference. And interestingly, that ratio of high PR to low PR in HRM, roughly 2.98, it closely matches the ratio measured in the mouse cortex, which is about 2.25 in the study they reference.
That's quite a coincidence, or maybe not a coincidence at all.
Maybe not. And furthermore, figure 8C also shows something else. The dimensionality of the high-level module, ZHH, actually scales up as you train the model on more unique tasks, while the low-level module's dimensionality stays pretty stable.
Suggesting the high-level module is adapting its representational capacity to handle more complex or diverse problems.
That's the interpretation, yes. It suggests an adaptive capacity in the abstract reasoning part of the model.
And crucially, this dimensional hierarchy, it wasn't explicitly designed into the model parameters or anything, right? It's an emergent property.
Precisely. That's perhaps the most critical point. They ran a control analysis, shown in figure 8E and F, using an untrained network, random weights, and in the untrained network, no hierarchical separation at all. Both modules had low and nearly identical PR values.
So it learned this structure.
Exactly. It confirms that this dimensionality hierarchy is an emergent property. It arises as the model learns to perform complex reasoning. It wasn't pre-programmed, and this is highly significant because it suggests HRM might be avoiding something called neural collapse.
Neural collapse, that's where representations in deep networks become overly simplified or redundant, right? Limiting learning.
Exactly. They converge to low-dimensional subspaces, which can hurt generalization and flexibility. HRM, by maintaining this high dimensionality, especially in its higher module, seems to avoid that trap. And that high dimensional representation in higher modules is considered crucial for cognitive flexibility, just like we think it is in our own prefrontal cortex. So in essence, HRM really feels like a significant step towards more general-purpose reasoning systems. By leveraging these brain-inspired ideas hierarchy, multi-timescale processing, it achieves computational depth, efficiency, stability, and it tackles problems that are currently intractable for even very large LLMs. Its ability to achieve what looks like practical Turing completeness, to adapt its reasoning strategies depending on the task, and then to spontaneously develop these fascinating brain-like representational hierarchies, it really feels like a potentially transformative advancement.
It absolutely does. This work seems to directly challenge the prevailing paradigm in AI, which often feels like it defaults to just scaling up existing non-hierarchical architectures, brute force scaling. And it poses a really interesting question. If even relatively small, brain-inspired models like this can learn such complex, diverse algorithms from minimal data, what new frontiers could we unlock by leaning even more into the fundamental principles of biological intelligence? And maybe even more profoundly, what does this imply about the very nature of thought in artificial systems if we can start to observe these emergent, adaptive, high-dimensional structures that seem to mirror our own cognition? It's a lot to think about. We definitely encourage you to delve into the paper yourself, grapple with the details, and ponder the implications. Thank you for joining us for this deep dive on AI peer review. Until next time, keep exploring, keep questioning, and keep learning.